So welcome to Current Electricity 2. We've done a lot of physics over the last semester, all about the past, but here we keep it current. Okay, well, I'll work on that. I'll send that one back to my writers, and I'll have a funnier pun for you on Monday. Current Electricity 2. Today I have two big goals. Two big goals. There will be a couple of different equations, but the big things I'm looking at, voltage and resistance. There will be other terms that I bring up. They are all in order to understand voltage and resistance. Now, this homework, if I recall correctly, I pulled off this homework. It's the first week of class. I kept it short and simple. The terms that I'm introducing today will be big on next semester, next week, and will big on next week and moving forward. Voltage and resistance and current are something we'll deal with pretty much every class for a month. But I do want you to have some perspective of what we're doing here. There will be several terms to learn. Focus on understanding voltage and resistance and use the other things that I introduce to understand them better. Maybe that's vague. Let's jump in. Oh, right. Also, I'm going to front load this lecture. I'm going to introduce stuff fast, all the stuff, and then we'll go, most of the stuff, and then we'll go through it and apply it and make some more sense of it. But I'm going to give definitions and an analogy, and then we'll come back to this and hit it from 50 different applied angles. Voltage, our first and biggest concept that's going to be, well, even more than a month. Voltage keeps popping up again and again. I'm going to define voltage. First off is the stupidest named term in all of physics. Voltage has 5 different names that I know of. I think I've seen 3 different symbols for it. Voltage, electromotive force, EMF, potential, electric potential. Basically, if you don't know what something is, guess it's voltage. Well, no. But all of these terms are synonymous. If you hear any of these terms, read any of these terms, it's voltage. I do my darndest in here to refer consistently to one term, voltage. I will call it voltage whenever. I don't think I'm going to forget and use another term. But in reading the textbook, I think they call it electric potential. Reading the online textbook, I think they call it EMF and electric potential, the free online resource. Yeah. So you'll hear, if you go to YouTube videos, hell, I don't know that Saki won't refer to it as EMF from time to time. So watch out for this, the terminology. Voltage. It's all voltage. It's all the same thing, just different words. Okay, what is voltage? Let me define it. Let me give an equation in words and then write it down. This is particular to circuits. Later in the semester, when we talk about static electricity and there is no circuit, I'm going to modify this definition. We'll get a more generalized version of this. But for now, for this first month of physics, I want you to think about a circuit has a battery, a power supply, a solar panel, has some electronic components, and electricity is pushed by the battery or whatever through the various components. We talk about the voltage dropped across each of the components, the voltage gained by the battery across each part in the circuit. Voltage drop is equal to how much the energy changes for 1 coulomb of electric charge. It is that ratio of energy to charge. It is the share of energy that 1 coulomb of charge gets. So when I say 1 volt, I'm saying 1 joule per 1 coulomb, 1 unit of energy per 1 unit of charge. In chemistry class, you guys deal a bunch with, calories per mole in reaction, right? You release that much specific? No, it's not specific. That's something else. What do you call that? When you calculate for a reaction, calories per mole, what is that? Huh? Associated energy? Okay. Association energy. Sure. Okay. So association energy and voltage are directly convertible. Disassociation. Okay. Disassociation. Not that association, disassociation. So that's directly relatable to voltage. Think about what that means. Who in chemistry has calculated calories per mole? Who remembers having calculated calories per mole? No? Okay, maybe I won't make that connection then. For those of you who remember doing that, that is directly relatable to voltage. The energy that each reaction or mole worth of reactions releases. Okay, so here's another analogy. You guys presumably know all about economics, being economics. Wait, no, you're not economics students. But you've heard about, GDP, income, gross income, and population, duh, right? Population countries. An analogy for voltage is per capita income, which is, it's been 30 years since my last economics class. I think it's the size of the economy divided by the population, right? Anyone have econ recently? Good. Okay, so per capita is not the total size of the country's economy. It's what fraction the average person gets, right? Who's heard of per capita income? Oh, fair number. Okay. So per capita income reflects the average amount of money that each person gets. Per capita income is, if I can make a very broad generalization here, Switzerland's got a medium-sized economy and only like 5 people in it, right? Very small population. Well, I don't know. It's been a long time since geography class too. Small population, medium-sized economy. Tell me about China. Is China's economy bigger? Yeah, it's the second largest in the world, but China's got 1 billion people in it. So the average Swiss person's got a lot more cash on average than the average Chinese person. Now, humans are pretty bad about being equal when it comes to money and everything else. I'll tell you this, electrons are hardcore communists. Hardcore commie pinkos. They share their energy very evenly. So the size of the economy is the total amount of energy. The voltage is the energy per electron. And at a given place in a circuit, all those electrons at that place are going to have the same amount of energy, the voltage times their charge. As an equation, we can say voltage equals energy per charge, energy divided by charge. And therefore, we can make the very difficult algebraic step, energy equals voltage times charge. Hopefully I haven't lost anyone there. That is to say, if you've got some charged particle feeling some voltage, you can calculate how much energy it has by multiplying its voltage times how much charge it's got. Yeah? That's not so bad. I'm trying to connect this with with circuits. What I just said is bad because I'm referring to individual charges. Okay, what I should say is the energy lost by some amount of electricity, some amount of current flowing through a component is the voltage drop across that component, the change in voltage from one side to the other, times how much charge is flowing through. Hey, what happens if I divide energy by time? What's that quantity? Anyone remember what a joule per second is? Anyone remember what energy per time is? Watt that is? Watt that is? Anyone heard of wattage? The rate at which energy is transferred is called wattage or power. And what happens if I divide both sides of this equation by time? right? Yeah. What's charge per time? Oh, come on, you need to know this. Current, yeah. So voltage times current equals the rate at which total energy is transmitted, is electrical power. From the perspective of a circuit, power is the oomph of the electricity. Power is most directly related to the loudness of a speaker, the brightness of a light, the heat dissipated by a resistor or a heating coil or whatever. Eh? So if you want to know how hot, it's not exactly temperature, but if you want to know how hot something gets, the electricity is flowing through, you could use the current through it times the voltage across it. That's how much energy is being dissipated or stored in it for that matter. The rate at which energy is being changed. We'll deal with power. Power is, as you see, just a consequence of, I rearranged the definition of voltage and divide by T. Power isn't really so sophisticated. It's not really a different equation, but we will use it from time to time. I'm going to concentrate on voltage and voltage and resistance and current though. Okay, so wait, one more analogy. I promise this is the last analogy. But it's important to get a sense of these things. Voltage is how much you suck on a straw. Imagine taking a straw and sucking or blowing on it, right? What do you have to do with your lungs to blow air through a straw or anything? Don't you have to press down with your lungs, compress your lungs, increase the pressure in your airway, right? Or to suck on something, you need to decrease the pressure by expanding the volume, PV equals nRT. Decrease the pressure inside your mouth, airway. Okay, so very importantly, voltage is the difference in pressure from one end of the straw to the other. For a straw, if I'm just blowing out into the air or whatever, the far end is at atmospheric pressure, whatever number of bars, 1 atmosphere, 15 pounds per square inch, right? The inside is whatever my mouth is, whatever I'm pushing with my diaphragm with. Okay, so pressure, very importantly, pressure doesn't matter unless it's different from one side of the straw to the other, right? If you put 15 pounds per square inch of pressure on the left and the right side of the straw, is air have any incentive to flow? No, right? If I compress my lungs and put more pressure on my mouth side than the far side of the straw, you blow out. If you suck in, you're decreasing the pressure on this side, it goes in. That's voltage. And very importantly, why I'm talking about drop or gain, because voltage itself doesn't do squat unless it's different from place to place. The change in voltage is what's vitally important. How much voltage is different from one place to another? Huh? Yeah, it's how much energy is lost or gained. Remember, in the last semester, we talked about potential energy. This cup here has 1 joule of 10 joules of potential energy. Does that do anything? But if I let this fall, if its potential energy changes, then something's happening. Just having a voltage doesn't do squat. You can hang from, don't do this, you can hang from a high tension power line. You can hang from a 455,000 volt transmission line with zero effect. As long as the other end of your body isn't touching the ground, isn't touching 0 volts. If your top is at 455 kilovolts and your bottom's at 0 volts, you're going to be crispy fried chicken real fast. Yeah? Voltage itself, if I just dangle from the transmission line, my whole body will be at 455,000 volts. That's the standard for US transmission lines. But that doesn't do anything. Being at a voltage doesn't drive a current. If there's a difference in voltage from one side to the other, that's like if both people pressurize a straw on both ends. That's weird. Okay, whatever. If both people pressurize a straw from both ends, the air doesn't go from one person. That's kind of yucky. Never mind. Ignore that analogy. Lady and the Tramp. Lady and the Tramp. They both pull on the spaghetti strand until they kiss. Does the spaghetti strand move from one person, one dog to another? No, because they're applying equal pressures, equal pulls from either side. Question. Yes. Yes. Yes, absolutely. Questions about the meaning of voltage at this point? Great. Google question. Hey, here, let me see if you were paying any attention. Jujel question A. What are the units of the quantity electromotive force? What the? There's no clicky. Oh, for dog's sake. Oh, thank God. Oh, it is recording. And remember, once you put it in, hit submit right away. Don't wait till the end of class. Good. I don't see a single wrong answer. It's like people are paying attention or something. I like that. Oh, it makes me happy when you get things right. Voltage! Voltage! EMF is voltage. There was one wrong answer. It's not wattage. Wattage is power. Wattage is energy per time. Voltage is energy per charge. So voltage is EMF. It's another name for it. All right? Okay? Now, we've got voltage, we've got current. Hopefully, I've given you an intuitive sense of what they are so that you recognize that they're very different sorts of things. Very important. You must be able to have a feeling of what voltage is, what current is, and how they differ. That will be midterm 1 questions. There will be multiple midterm 1 questions that go back to understanding them and the difference between voltage and current. Do not mistake one for the other. Current is the flow, voltage is the push. But every electronic component has some relationship between voltage and current. Every electronic component, every device that I know of, has a relationship between voltage and current, and every component is different. Yeah. Well, voltage isn't, the river doesn't get dammed if there's a complete circuit. There's going to be some flow. There's always going to be some flow. If you want to use a water analogy, you could talk about gallons per second, gallons per hour passing a given point, how much water is passing along the river. And voltage would be, I guess the difference in voltage is the height difference from one end of the river to the other. You know, if you've got a stream flowing down the side of a mountain, that's going to flow real fast, right? If you've got a river that's on a plane that's barely inclined, you know, there's got to be an inclination, an altitude change for a river to flow at all, right? So the altitude change, potential energy change would be the voltage there, the change in voltage. So the height is the voltage, the change in height, the altitude change is what's important in driving the water. And resistance is what I'm about to hit in 1 second. Yeah. Okay, so more analogies later. Thank you for bringing that up. But going back to what I was saying, I want to emphasize what I'm about to show you with resistance is true for one kind of component and one kind of component only, the resistor. Okay? It is very common for students to think that V equals I times, think that the equation I'm about to give you is a universal, always true equation, and they apply it in situations that make no sense to apply. This is true for one kind of thing, the resistor, resistance. It applies for resistors. And Ohm's law, what I'm giving you here, is a statement about resistors. When we talk about capacitors, there will be a different voltage-current relationship. When we talk about inductors, there will be a different voltage-current relationship. There is no voltage-current relationship for batteries. Batteries just get a constant voltage. Well, I mean, I guess you could say that the voltage-current relationship is the equation y equals 0x plus b. It doesn't depend on current. Okay. So, do you guys know what proportionality is? Say something is proportional, what's that mean? No, it doesn't mean equality. Equality is not proportionality. What's proportionality? If x doubles, y doubles. The equation's a straight line passing through the origin. Y equals mx, not y equals mx plus b. Linear, y equals mx plus b. Proportional, y equals mx. The everyday definition I give, though, is if x doubles, y doubles. If x triples, y triples. If x halves, y halves. Note, by the way, to say that voltage and current are proportional. The voltage drop in a resistor, the voltage drop in a resistor is proportional to current, means that even if you've got an itsy teensy bitsy switsy little voltage, that will drive some current through a resistor. It's a common mistake for beginners to think that resistors block voltage. They're not a dam. Sorry, my language. They're not a dam. They're a rapids where you got lots of boulders. It throttles. Resistors throttle current. Resistors limit current, but resistors don't block current. A diode is a dam. We'll talk about that later. Okay, so this statement, V equals R times I, V equals I times R, says that the change in voltage from one end of the resistor to the other, as current flows through the resistor, the change in voltage is equal to the resistance of the resistor times the current in the resistor. Where'd my pen? There it is. Ah. Okay. I should also introduce, this is the appropriate place in the class to introduce the symbol. You may, if you look at alternate sources online, you may also see resistors are rectangles. That's the European standard. But I'm always going to draw it like this. Our textbook draws it like this. Exams will have this symbol. This is the symbol for a resistor. If you've got this symbol, you're allowed to use that the change in voltage across it is IR. If you don't have this symbol, don't plug in IR. It doesn't make sense. Okay, so. Let me divide both sides by I and interpret this in a different way to give a better sense of this. What does it mean for resistance to be voltage divided by current? Here's another way to define resistance. Resistance is how much push you have to get a given amount of flow. How hard you have to push something to move at a given rate. How hard you have to push something, voltage, to get a given amount of flow. I mean, if you're drinking a milkshake, how hard do you have to suck to get an actual mouthful per second or whatever? That's resistance. In the milkshake analogy, resistance is the difference between a cocktail stirrer, a regular straw, a boba straw, and drinking through a garden hose. right? The tinier the straw, the more you would have to suck to get a given amount of flow rate. Now, wait, before I put this up, I want to caution you. There's an equation about to come up. MCAT likes to ask this equation, which is ultimately why I'm putting this on. Let me start by saying, what's the difference between a cocktail stirrer, a regular straw, a garden hose, a boba straw? What's the big difference? The size, the shape. Electricity. What if you put 15 boba straws one after the other and you suck on one end? You think that'd be as easy to drink through? No. So length also matters, although we maybe don't know that because we don't normally have different lengths of straws, right? Okay, but length also matters. Resistors aren't straws. There's also something that is getting in the way besides just the physical dimensions. If you put some kind of like a foam inside of the straw or whatever and drank through that, that would be a resistor. So what matters about the foam? How thick it is, right? The density of the foam material. These are the three things that affect the resistance of a resistor. Its size, its shape, and the material it's made out of. Before I show you the equation that relates these, write this down as a sentence. Three things that affect the resistance of a particular resistor are size, shape, and material. Now, virtually all resistors, no, not virtually. Every resistor I've ever seen is a cylinder. Do you guys know that you could just buy a resistor? They're 5 cents at master.com plus $50 shipping. Oh, yeah. Resistors, when I say a resistor, they're just things. Their value is printed on the side in a special code, and it has a constant amount of resistance till you heat it up a lot. It does change with temperature, right? But the resistance of a resistor is a property of the resistor. That's a thing you should write down too. I've been mentioning this in the way that I talk, but this is worth making a specific point. The resistance of a resistor depends on the properties of the resistor, not the electricity flowing through it. Again, best way I could think of to put this is the resistance of a resistor depends on the properties of the resistor, not the voltage and current, not the electricity applied to it. I got this equation with V, I, and R in it. What happens if I double V? Does R double? No. R is constant. What must happen if V gets twice as big? I gets twice as big. What happens if I have a resistor and then half as much current is going through it? Does that mean the resistance has increased? No. If I have got a given resistor, its resistance can't increase. Halving I must do what to V? Google form, what are we on? B? Google form B. If I have half as much current in a resistor, how much does its resistance change? Google question C, if I have half as much current in a resistor, how much does its voltage change? Google form B, if you apply half as much current to a given resistor, how much voltage? B was how much does the resistance change? C is how much does the current change? Yes, absolutely. Did I say current? I said current. I said current. If current through a resistor and C is same question. If current through a given resistor halves, its change in voltage will. Can you read my writing? See what I'm saying? If current through a given resistor halves, its resistance will blank. If current through a resistor halves, its voltage will blank. Please read, by the way, this is very annoying to me. If I put a big B before a question, that means put this in Google form B. If I put a C before the question, answer it in C. I've got people answering in D. Don't, listen. Okay, turn to your neighbor and argue about this because half the class didn't hear the point that I just made. Argue about these 2 points, please. Okay, what's the last line in your notes say? The resistance of a resistor depends on the properties of the resistor, not the electricity applied. Yeah, that's what I said. The resistance of a resistor doesn't depend on the electricity. So if I have the amount of current, if half as much current is flowing through a resistor, how does its resistance change? It doesn't. I just said that the electricity doesn't control the resistance. A third of you, listen up. Okay? Actually, everyone listen up. Think about this. So if I becomes half as great and R don't change, does V double? Halve? Become a quarter? It halves. Half over a half does not change. Voltage drop is half as great if the flow is half as great. You can't change the resistance of a resistor. You can heat it, but the voltage through a resistor, the current through a resistor doesn't change the resistance. The current through a resistor is proportional to the voltage through the resistor. Half as much current comes from half as much voltage. That's a true statement. So, las respuestas correctas, the correct answers were doesn't change and becomes half as great, or halves. Okay? More or less, más o menos, meow to vinegar. Here's the equation that relates the size, shape, and material thing that I said. You want to actually figure out the resistance of a resistor. Well, you look at the value printed on its side. But here's how you could calculate this in principle. Or if you've got some sample of material, a wire, wires can be resistors. And you want to calculate its resistance. Here we go. This, by the way, is not P. Don't call him P. This is rho. Anyone in a fraternity with or sorority with rho in it? No. There's only one? There's only one that you know the names of all the sororities and fraternities? I'm impressed. Good memory. All right. So the resistance of a material, the resistance of a given resistor depends on the material and the size and shape. The material constant is called rho, and the material constant doesn't depend on anything except temperature, but I'm not going into that in this class. We're not calculating the change in resistivity. For our purposes, at room temperature, rho is based entirely on, is this steel, copper, carbon, iron, what? Rho is a property of the material. So if I double the voltage across a resistor, how does rho change? It doesn't. As long as the resistor is made of the same material, rho can't change. Now, I apologize. Electronics is full of this, but the name is terrible. Resistance sounds just like resistivity. They're not the same thing. Resistance is the resistance of a given resistor. Resistivity is the property of the material that it's made of. Okay. Where do you get rho from? You look it up. They're tabulated. You look it up in a table. You Google it. It's a constant. It's measured probably 100 years ago and written down, and that's its value. L and A. As I said before, the every resistor I've ever seen, and I've seen a bunch of resistors, is a cylinder. Google form E. Do you remember the formula for the area of a cylinder? Cross-sectional area? What? Question, what? We're on question D. We're on question D. Thank you. D. Give me D. The Google question D is, do you remember, tell me, the equation for cross-section area of a cylinder? Not surface area, not the total around area, but the, look, I'll draw the damn thing. Here's a resistor. I want you to tell me, do you know the formula for that area? Hint, it's a circle. I'm glad I asked this because less than half of you remember circles. Okay. Ooh, some of you can type pi. Cool. Oh, you fixed it. This is Google question D. The correct answer is pi r squared. It's a circle. Pi r squared. Cross section is a circle. Pi r squared. You'll need that for my next question. If you got a cylinder, its cross section is a circle. Pi r squared. What's the length of a cylinder? Oh, the length. L, whatever. Hey, what's diameter? Do you guys know what diameter is? Google question E. Let me just check to make sure everyone knows what diameter is. What's the formula connecting diameter and radius? Give me the formula relating diameter to radius. Okay, well, you got diameter and radius. 2r, twice the radius of the circle is the diameter. Good. I'll take it. I mean, that's an algebraic operation that is legally allowed. You may but divide both sides by 2. I give you my blessing to divide both sides by 2. Okay. Got the geometry, got the algebra? Ready for a question? Here's a thinky question. Nope, sorry. I could ask 3 questions. Here's a are you listening question. This is Google question F, and I forgot to put this in form list sense. Tell me A, B, C, D, E for each of these. If you think the length of the piece of material is part of what determines the resistance, put A. If you think the length and the type, put A, B. Please do not type out the full sentences. That's tedious for me to look at. You can separate with commas if you wish. I'm not going to care about that. Yo. Okay. Tisk, tisk. All right, I'll take it. That's enough correct answers. Correct answer is ABC. I mean, look, go back to the previous equation where I say, here's how you calculate the resistance of a piece of material. The kind of material, the length, and the cross-section, right? If you've got an equation relating these things, then that's what determines them. That equation, the resistance of a given resistor, comes from those 3 things. By the way, how do we measure a resistance of an unknown resistor? In practice, what I would do is I would apply a known voltage and measure the current, or apply a known current and measure the voltage, but it's easier to get a constant voltage. So, what question is B only the answer to? If I asked you what determines rho? Exactly. Okay, Google G. OG. Read carefully, my dudes. And no, you don't need initial values. You can do this just based on reasoning. What? Yeah, a ratio rho 2 divided by rho 1 is a number. Think about what I'm asking is, by the way. What is the nature Hannibal Lecter said that. What is its nature? What is its essence? Follow Dr. Lecter's advice. Do you guys know Silence of the Lambs? I ate his liver with fava beans and a nice Chianti. Again, look at the question carefully. What term am I asking you to compare? What term am I asking you to compare? The resistivity of the two wires. What controls resistivity? Correct answer is one. Uno, eins. Da 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 da. Yeah? Did you think I was talking about resistance? Careful. Watch out. There are different things. Okay, now I'll ask the question that you thought I was asking. Ask yourself, if L gets twice as great, how does formula change? If D gets twice as great, how does formula change? This is a Google question. It's one. It's the same material. Rho just is the material constant. Remember what I said? It's tabulated. You got copper, and if you got another thing with copper, copper is copper is copper is copper. The area is not twice as big. Look at the formula you just wrote down for circles. Area does not double, my friends. Let me make this point carefully. If I double the side of a square, are there twice as many? Are there now 8 squares? No, there are 16 squares. If I double the side of a square, I get 4 times the cross-sectional area. In the formula pi r squared, if r becomes 2r, not equal, I should say that is not equal to the next line, pi times 2r, what's 2r squared? Is that 2r squared? No, 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 as my older child said as a baby. Okay, I don't tell you what r is, but if r is some value, area 2 is 4 times area 1. Yeah? Is that my final answer? No. Hold on a second, cowboy. Okay, what's the formula for resistance? To solve this problem, you have to consider 2 factors. What is length doing? What is area doing? if area doubles, if area quadruples, if area quadruples, what happens to 1 divided by area? If area becomes 4 times as great, what's R doing? If just area changing. If A gets 4 times as big, if you make the downstairs of a fraction 4 times what it was, how does the fraction change? Does it get bigger or smaller? Google form I. If I increase the downstairs of a fraction to 4 times what it was, does the fraction become a bigger or smaller number? I got some people not hitting enter. Scroll down, hit enter. Or maybe some people who have fallen asleep. Wake up! Okay, I'm going to compare the numbers. 1/2 and 1/8. Which is a bigger number? If I cut a pizza into 2 slices, I've got more pizza than if I cut it into 8 slices. I mean, if you cut the pizza, I just eat the whole thing. Okay, so how much smaller? Smaller is the correct answer. How much smaller is the pizza if I multiply the downstairs by 4? It is 1/4 as great, yeah? Right? If A becomes 4 times what it was, R becomes 1/4 of what it was. Okay, so A is not the only factor in R. A quadruples, quartering R. L doubles, what does that do to R? Just doubling R, just doubling L, what does that do? If you double the upstairs of a fraction, what happens to the fraction? It doubles, right? Now ask yourself this, if I put 2 factors together now, if I double something then quarter it, what have I done to the fraction? Let me see if you could do that in the Google form. Question J, if you double something then quarter it, by what factor has it changed? If I double something and then I quarter it, by what factor has it changed? This is proving challenging. Let's talk about this in practical terms. I've given you $100. Now you have a quarter as much. How much have you got? 25 bucks. Now you double that. What have you got? 50 bucks. You halved it. Yeah? If you double something, then quarter what you've doubled, you have half as much. 2 times a quarter is a half. Yeah? We're going to practice this skill a bunch of times. Reasoning not based on just calculating with a number, but calculating based on a principle, based on a formula, a relationship. If you ain't got this yet, okay. I do encourage you, if the fractions killed you, Khan Academy, something. Okay, so I'm going to introduce, we are not through this slide set. I do not wish to push through 7 slides in 12 minutes, but I do wish to use the time that we have to get a start on this. We'll pick up wherever we end. We'll pick up class tomorrow on Monday. I need to tell you properties of resistors and batteries. Well, I already told you a property of a resistor. The resistance of a resistor does not change. The current that flows through a resistor depends on the resistance of the resistor and the voltage across it. So V equals IR for a resistor. What about a battery? When I have a 9-volt battery and then I turn it on, what does it turn into? Does it become a 1 volt battery? No, it's called a 9 volt for a reason. It stays 9 volts. Yeah? The voltage of a battery is a constant. The voltage of a resistor is IR. The voltage of a capacitor is Q over C. The voltage of a transistor, well, we'll get there. Okay, Google question K. Voltage is energy per charge. Current is not energy. Electricity is not a defined term. Electricity is the chapter title. What property of electricity is energy? You know, it's like saying, is motion just is motion just height? Is motion just acceleration? Acceleration has a defined meaning. Motion does not. I can't answer your question. One side of your equation is undefined mathematically. Talk to me more about that afterwards. I want you to have an intuitive feeling for this. Okay, the correct answer is Ver. The battery keeps V constant. R goes up. What must I do to keep V constant? Correct answer is decreases. Now let me change the question. Battery is connected to a resistor. How does increasing the resistance of the resistor change the voltage of the circuit? Google question O for I love physics. Oh my God, so many correct answers. Yay. I say increasing the resistance just after I said you can't change the resistance. Let me perhaps reword the question. If I replace the resistor with one of higher resistance, there, that's something that's internally consistent. Or, as I said it, I heat the sucker. It'll... All right, this is better than last year. Not perfect, but better. What did I just say about batteries? Voltage stays the same. If a battery is connected to a resistor, the voltage can't change. Correct answer is it doesn't change. What I just said on the previous slide is V equals I times R. If V stays the same, well, then V still stays the same, even if I'm asking a slightly different question. Yeah? If I have a given resistor decreasing the current, increasing the resist, changing a given, look, it depends on what you're holding constant. If you've got a battery, the voltage is held steady. If I ask you about a given current flows through this, that, or the other resistor, it takes more or less voltage to drive that. You have to consider what is being applied, not just look at the equation and see, oh, left side equals right side. You have to consider what affects what. One last thing. No, 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 no. We're done. Get out of here. I love you. Bye. We'll do it on Monday. It's good. Huh? Oh, we'll do this on Wednesday. No class Monday. Celebrate Dr. King. Dream of a world where people listen to him. Have a second.